from browser-based LLMs that run faster and leaner on WebGPU, to privacy-preserving random forests that stay accurate even on sparse data, to a new way of turning lossy KV caches into exact LLM inference. Today's episode explores how AI research is solving real-world bottlenecks in performance, privacy, and reliability. We'll look at clever systems, designs, surprising trade-offs, and breakthroughs that push models to work better under tighter constraints. Stay with us, these papers show how much smarter AI engineering is getting. Let's explore the first paper, Llamas on the Web Memory-Efficient, Performance-Portable, and Multi-Precision LLM Inference with WebGPU. Llamas on the Web introduces LlamaWeb, a WebGPU backend for Llama, CPP, that targets browser-based LLM inference with static memory planning, performance-portable kernels, and broad quantization support. The key novelty is a design that eliminates dynamic GPU allocation by pre-allocating all buffers, including a fixed slot parameter arena and intermediate memory for flash attention and flash decoding, while streaming GGUF weights asynchronously from the browser's origin private file system without materializing them in the WebAssembly heap. Across 16 devices from 8 vendors and 10 models, LlamaWeb reduces peak browser memory by 29 to 33% relative to WebLLM and Transformers.js, and avoids the memory growth and tap crashes observed in those systems. For performance, it uses a templated shader library that specializes kernels by device features such as subgroups and subgroup matrix operations, and by workload parameters such as tile size, with tuning derived from an exhaustive sweep of thousands of configurations. On 4 GPUs, this portability layer improves decode throughput by 45-69% over WebLLM and Transformers.js. And on some systems, it matches or beats native backends. On Apple M4 Pro, it is up to 59% faster than Vulkan during prefill, and on Intel Arc B580, it outperforms native SYCL by 23% in prefill with WebGPU checks disabled. The paper also extends Llama.cpp's quantization ecosystem by implementing templated dequantization for 23 weight formats, including legacy Q4, 0, and Q8, 0, K-quants such as Q4, K, M, I-quants, and the new Q1, 0 format, enabling one kernel family to support many compressed models without format-specific rewrites. Let's explore the second paper, Lumberjack better differentially private random forests through heavy hitter detection in trees. Lumberjack tackles a specific failure mode in differentially private random forests. Fully random trees are privacy-friendly but collapse on deep, sparse tabular data, while greedy private splits are brittle and often incorrectly analyzed. The paper's core novelty is to build very deep random trees first, then privately prune them using a new hierarchical heavy hitter detector with error scaling O log h in tree height h rather than the O square root h sensitivity of naive node counting. The detector uses a middle layer query, monotonicity-based propagation of heavy, light labels, and an adaptive Gaussian sparse histogram thresholding mechanism, yielding a tight joint privacy analysis over the entire forest. In the forest itself, Lumberjack splits features uniformly at random, as in extra trees, prunes branches whose nodes are not sufficiently populated, and privatizes leaves with either the exponential mechanism for majority vote or Gaussian noise class proportions under ZCDP accounting. Empirically, on adult and 4 Folktables California classification tasks with epsilon in 0.5, 1, 2, 4, 8, and delta equals 10, -6, Lumberjack consistently outperforms prior DP random forest baselines, including diffprivlib, SNR, smooth sensitivity, and Suikonen, often by several accuracy points, and sometimes beating a non-private greedy decision tree at moderate privacy. The paper also reports privacy flaws in more than 10 prior DP random forest capers, and shows a lower bound indicating that some threshold growth with tree depth is unavoidable, making Lumberjack's logarithmic height detector close to optimal up to a square root log h factor. Let's explore the third paper, Vericache turning lossy KV cache into lossless LLM inference. Vericache reframes KV cache compression as a draft and verify accelerator rather than a replacement for exact inference. It runs the target LLM on a compressed KV cache to draft tokens, then verifies them against the full KV cache, so greedy decoding output is identical to full KV inference. The paper shows why this is necessary by measuring sequence-level KL divergence growth on Qwen3 Coder 30B, where KVZip 4 times and TurboQuant K4V3 accumulate roughly 0.023 nats of KL per decoding step, which compounds to about 6 nats after 250 tokens and causes functional collapse on Swebench Lite and complex Funkbench, even when token level F1 remains above 75%. Vericash's key novelty is system design. Cross-resource staggering overlaps compressed KV drafting, which is HBM bandwidth bound, with full KV reload and verification, which are interconnect and compute bound, and an extended draft horizon exploits unusually high acceptance lengths of 2540 tokens per round, far above typical small model speculative drafters 2-3. Built on VLLM and LM cache, with a uniform compressor interface spanning 7 methods including KV-zip, KIVI, KV-quant, and rotate KV, Vericache reaches up to 4 times higher throughput than full KV inference on long context decoding, and up to 2 times on remote prefix caching, while keeping KL below 0.01 nats from hardware nondeterminism and preserving exact quality on tasks like function calling, long-form generation, and code synthesis. That's a wrap on today's AI paper highlights. Thanks for watching.